Okay, we will start the second keynote of the conference. The keynote speaker is Sachiko Yoshihama. She's a senior technical staff member and senior manager at IBM Research Tokyo. And she's been working as a software engineer after graduating from Yokohama National University in Japan, and then joined IBM TJ Watson Research, and then came back to Japan and has been working. And she also worked in China, IBM over there. And recently she's been focusing and leading the R&D effort in Japan on blockchain. So please join me welcoming Sachiko.
Thank you very much for a kind introduction. Hello, and thank you very much for giving me an opportunity to talk about our blockchain activities in IBM and IBM Research. So today I'm going to talk about blockchain as a business platform, mainly focusing on the opportunities and the challenges in the blockchains in industry, as well as some of the research work that we do in IBM Research Tokyo to address some of the programs. And a brief introduction of IBM Research and me. So in IBM Research, we have about 3,000 researchers worldwide across 13 research laboratories. That is about 1% of the population of IBM employees. And many of the labs are working on some kind of the blockchain project, such as development of the Hyperledger Fabric, one of the open source blockchain platforms, as well as working with clients in many industries to do a proof of concept pilots, or to actually develop the solutions that IBM is advocating. So here is the outline of my talk today, blockchain for business, and technical challenges, and our work on smart contract generation. So I don't think I need to repeat this too much in this conference because everybody seems to be familiar. But there are two distinct types of the blockchain: public blockchain and permission blockchain networks. And the public blockchain is a very popular network, but in the industry we focus mainly on the permission network because of the requirements for the business or regulations. So in the permission network, only permission parties can join and to do a transaction of the business level on top of the blockchain, so which can transform the cross-organizational business processes to make it more efficient or to create new values and so on. And there are many business-oriented requirements which lead to the choice of the technology, which is more like a traditional distributed database or transaction systems rather than the proof of work type of the really blockchain-like technologies. But it makes it easier for the businesses to adapt the technology as a kind of extension or the next step to their IT infrastructure. So in order to address such requirements for the permissioned blockchain network, IBM worked with partners to launch the open source community called Hyperledger, which is a Linux Foundation project. So Linux as an open source community is hosting multiple communities like this one as an umbrella. And we launched this community in 2015 with 70 founding members. But after that, the number of the members have rapidly increasing, and now it has more than 260 members. And Hyperledger is an open source community, open source and openly governed collaborative effort to advance cross-organizational, cross-industry blockchain technology for businesses. And because many parties are working on this technology as a common platform, it will help us to develop the technology in a more rapid manner with high quality than doing proprietary project within each company. And under the Hyperledger community umbrella, there are 13 projects right now. This picture comes from the Hyperledger Global Forum December last year, so it's already still a little bit outdated. But mainly there are frameworks and tools. And on the framework, we have blockchain platforms such as Hyperledger Fabric, Iroha, Sawtooth, and Barrow, as well as some the decentralized identity platform like Hyperledger Indy. And on the tool side, there are multiple projects focusing on different aspects of the tools for blockchain, such as the Caliper as a kind of performance benchmarking, Trello as DevOps tools, Composer as an application framework, Explorer as a blockchain viewer, and Keynote as a interledger connectivity, and Ursa as a shared cryptographic library, and so on. And then these activities are very active. So after 3 years since launch, there are already 56,000 commits across 13 projects, and there are nearly 800 contributors, and so on. So as you can see here in these statistics, this collaborative development of the open source blockchain platform is widely accepted by the industry as a kind of common platform to pursue the industry use of the blockchain. And IBM first developed so-called open blockchain as an open source platform and contributed it to the Hyperledger community, which became a foundation of the Hyperledger Fabric, and Hyperledger Fabric has 4 key capabilities or key characteristics like this one. So in the ledger part, Hyperledger Fabric supports the blocks as any ordinary blockchain platform, as well as a state database, which is essentially a key value store that can store richer data on chain. And the smart contract is supported in the name of chain code. And each smart contract runs within a Docker container so that it's kind of language agnostic mechanism to support different kinds of the languages as smart contract. So now it supports the various general purpose languages such as Java, JavaScript, Go language, and Java. And also there is an ongoing work to support Ethereum bytecode as a smart contract. And on the consensus part, because of the some reasons, the proof of work type of consensus is not applicable to the business level blockchain. So that the Hyperledger has been adopting the distributed multi-party consensus algorithms as kind of core consensus mechanisms. And the security and privacy is very important for business use. So it uses PKI-based membership management and that supports various privacy protection mechanisms such as encryption and ZKP-based identification. So, and the Hyperledger Fabric initially appeared in 2016, and in 2017 it drastically changed its architecture and published as an version 1. And after version 1, it has been evolving by adding new capabilities, such as adding different languages for smart contract, and the private data collection for protecting privacy, or identity mixer for anonymous authentication. And early this year, we have released version 1.4, which include a lot of operational metrics and logging improvements. And it's kind of the last version in 1.x. And now it's under the long-term service support. And now the community is working on the second major version, the version 2, which include a lot of the changes and improvement. And the main changes here will be things like improvement of the SDK or life cycles, as well as supporting the tokens on Hyperledger Fabric will be one of the key features, and the supporting the raft consensus, in addition to the original ones used. So by using this Hyperledger Fabric or other permissioned blockchain networks, there's blockchain use cases have been expanding. So if you look at the industries, it's initially started with the traditional coins or token type of the transactions, but extended its scope to the more general purpose data sharing use cases, such as sharing KYC, AML information between the banks or contract management and supply chain, or more aggressively use smart contract to automate the cross-organizational business processes, such as those in financial market. Let me talk about a couple of the use cases that we worked in Japan with clients in Japan. So the contract execution is one of the promising use case of blockchain with a rich smart contract capability. So the idea is to use blockchain as a repository for recording the legal documents exchanged between the parties, and use smart contract to automate the contract execution process. So for example, this is a very simple example of the purchase order. Actually, so even for the simple purchase order, there are multiple documents involved. So for example, there is a master agreement between companies, and for each purchase, there will be a purchase order issued by the buyer, and after the item is shipped and accepted by the buyer, then the delivery report will be issued and accepted, and the invoices will be issued, and the payment will be made. And on this process, there has to be multiple actions and consistency checks to take place. So for example, if the invoice is issued, we want to make sure that the price is correctly capturing what agreed by the purchase order, or the shipment received is actually correct, and so on. And today, all the humans are mostly doing these manual checks, but smart contract can automate these processes to drastically make it more efficient. And another use case we worked with an exchange in Japan is proof of concept on the financial market post-trade processes. On the left-hand side, you see a simplified view of today's financial market. So, if you go to the stock market, you may place sell order or buy order. And if those sell order and buy order matches, the trade gets executed. And the post-trade process happens after the trade gets executed. So basically, after the trade is agreed, the settlement has to take place. And in the financial market, settlement takes at two places. The one is a settlement of securities, which is currently managed by the Central Security Depository as a kind of centralized database to record the ownership of the securities. And the settlement of the security happens by changing the ownership of the securities on this database. And the second part of the settlement is the money settlement. And you basically, the buyer pays the money to the seller, right? So, and the difficulty is that there is a requirement of the delivery versus payment, meaning that this settlement of the securities and money has to take place together, or if one fails, the other has to fail. And then in this POC, we implemented this process on blockchain by using a smart contract. So now the central database managed by the Central Securities Depository was moved into the blockchain as a distributed ledger. And this settlement of delivery versus payment was automated by using the smart contract. And also we automated some of the corporate actions, such as dividend and stock split, using a smart contract. And in this chart, you have only one layer of the banks as a brokers. But in the real world, this network is actually much more complicated. It can scale to like 10 layers of the banks, communicating each other. So there's a lot of the inefficiencies. So the blockchain shows the potential to improve such an cross-organizational business processes in complicated network technically. You may still think that there are only proof of concepts and not real business happening with permissioned blockchains. But that is not true. The real blockchain production systems are emerging and growing. So these are the examples that IBM is advocating. IBM has been working on the global trade, food traceability that I'm going to talk about later. And also, we are working with European banks to do a trade finance on blockchain to support the financing of the small and medium enterprises in Europe. And also, we just launched the IBM WorldWire, which is a remittance over blockchain built on top of the Stellar blockchain network, and is supporting digital identity network. So let me talk about food supply chain network called Food Trust. So the issue of the food trust is very severe. Study says that there are only 1 out of 4 consumers trust the food ecosystem, and there are many issues. So for example, on average, 1 out of 10 people get sick from the foodborne illness, and 420,000 people die from that. And 80% of the consumer product goods businesses are paper-based, or even if digitized, it's something like Excel spreadsheet sent over email or something. So it's very inefficient. And there is an issue of food waste. 1/3 of the fresh food is thrown out because they are considered unacceptable while they are actually okay. And 1/5 of the seafood samples are mislabeled worldwide. And interestingly, this number gets worse in the New York City. 43% is mislabeled. This, there is a common root cause for this, which is a lack of the trust and transparency in the food ecosystem. So today, the food ecosystem is very complicated and inefficient. There are many players across industries, such as farmers, fishers, logistics companies, manufacturers, retailers, restaurants, and so on. And the data is siloed within each company. So the access to the data is often limited and have high cost. And when the information is exchanged, this exchange happens between each pair of the parties. So if you want to access somebody's information that is distant in this complicated food supply chain network, it takes a lot of time and cost to access. And then most transactions are still paper-based and very inefficient and have an opportunity to fraud and mistakes. And because everybody maintains their own record or ledger of the things, when there is a mismatches or the inconsistencies, it takes time and effort to reconcile. So the IBM Food Trust is a blockchain-based solution to resolve this problem by using blockchain as a kind of distributed ledger for recording the food supply chain information. And it provides key capabilities such as tracing of the goods from the upstream and downstream across the supply chain, and the certification, which is a solution for digitizing audit and certificate information and making it easy to share with supply chain partners. And Fresh Insight is a solution to provide a real-time visibility into aggregated supply chain data to optimize supply chain processes to improve shelf life and so on. And initially, in the early stage of this project, IBM has conducted a kind of Mango pilot with Walmart in the United States to test how much time does it take to trace back the origin of the sliced pack of mango, which is on the shelf of the Walmart supermarket in the United States. So, you can imagine that you trace back to the logistic company, then go back to this manufacturer and go back to the exporter and so on. Then it took actually nearly 1 week to trace back to the original farmer. And you can imagine that if this becomes a big problem, if there is things like food contamination, that you want to know which other product might get the contaminated materials that came from the same farmer, for example. And by using IBM Food Trust, it takes only 2.2 seconds to trace back all the information. And this IBM Food Trust has officially launched in October last year, and initiated by Walmart and adding large players such as Dole, Nestle, Carrefour, and so on. And now there are 80 or more clients, which is part of the network, and including the majority of the Walmart suppliers. So now it has become one of the largest non-cryptographic blockchain networks in the world, and more than 5 million food products on retail shelves are recorded, and the 1,200 stock keeping units representing 4 million transactions, and 200,000 traces have been conducted to date. And let me briefly talk about the second use case, trade lanes, which is kind of similar to the food supply chain in terms of the focus on the logistics part, but more focus on the global trade inefficiencies. So today, there are more than $16 trillion worth of the goods are shipped across international borders each year, and 80% of the goods that we use every day are carried by the ocean shipping industry because of the rapid globalization. But the biggest cost of the global trade is around border administration because of the inefficiencies. According to the study of the World Economic Forum, if the border barriers is reduced and removed, the global trade could increase by nearly 15%, which could result in nearly 5% growth of global GDP. And actually, removing the border barrier have larger impact than completely removing tariffs, according to their study. And again, here is a case study of the global trade shipment. So we analyzed the shipment of avocados from Mombasa, Kenya to Rotterdam in Netherlands. So Mombasa is the second largest city in Kenya, which is along the coastline. So we investigated how many actors and information interactions happens in this trading. So there are on the one shipment of avocados, there are 3 actor companies involved, and there are 100 people involved, and there are 200 information exchange involved. And many of them are still paper-based and manually done. So you can imagine how inefficient it is. So the global trade solution is, again, changing this mechanism by using blockchain, to use the blockchain as a kind of the distributed ledger transparency of the record to improve the transparency and efficiency of exchanging the documents related to the global trade. And yeah, so now there are 2 types of the data. One is on the bottom part, foundational data comes from mainly the ocean carriers. That's the core data needed to track and manage the shipment end to end. And there are more than 20 million containers tracked today, which is about 20% of the global container shipment volume. And on top of that, we have an enrichment data comes from the connected logistics members, such as port and terminals, inland transportation, and government authorities. And and this is kind of the network players. As you see, nearly 60 or more members have connected to the network already, including the many ports and terminals, and 3 major ocean carriers, and so on. And in addition to that, many other players, like rest of the major ocean carriers, as well as the government authorities, in the process of connecting to the network, that consists of the 500 million shipping events per year, which is 10 million shipping events per week. So again, this is one of the largest growing non-crypto blockchain network in the globe. Okay, so let me next talk about what are the technical challenges you face when running the production level business blockchain. So of course there are functionality issues, like does blockchain provide all the necessary functionalities, but there are more non-functionality requirements, such as reliability, including availability and resilience to and recovery to the fault, including wide area disasters. And operability, as you record so much information on blockchain, how much data get accumulated and where is a big question that we have to address while designing the enterprise level blockchain. And can data be archived, deleted, or backed up and recovered is another operational questions. And can users or peers be added or removed dynamically, or can their permissions dynamically changed over time as the membership have changed? And performance is one of the still biggest challenge in many of the blockchain platform. Not only just the throughput and latency question, but how can we deal with the peak transaction, or if there is any performance degradation after a large amount of data gets accumulated, and also the scalability in terms of the number of the peers and users. And the maintenance ability, can we update smart contracts and application, or can we update blockchain platform without stopping the system? And the security is also a very serious problem. Is it resilient to tampering or impersonation? Can data privacy be protected? Can access control be enforced in an appropriate manner, or can we deal with compromising a crypto system? And of course, there are non-technical questions, such as what is a business value, what is a business scheme that we want to build on blockchain, and what is a governance model, can we meet regulatory compliance, and so on. Let me pick 4 technical challenges to talk about more details. So finality, privacy, scalability, and safety of smart contract. So the finality is a concept often used in the financial industry, which means that once settlement or payment is completed, it is irrevocable and unconditional. That's a very important concept for many financial industry players, that they cannot stand without having it. And as you know, the proof of work or proof of stake, or most of the proof of something families of the consensus algorithms cannot guarantee finality because of the probabilistic nature of it. Because in the proof of X type of the algorithms, there is always a chance of the fork in the network, which can lead to the lack of the finality. And by taking advantage of this capability, actually, so-called 51% is increasing. And you might have observed that there are many instances of this kind of attack to the altcoins recently. It looks like the high-value altcoins with smaller hash powers are mostly targeted because it's a soft target. And as the coin prices fluctuate, there is a growing risk of cryptocurrency ecosystem to not to be able to survive this trend, because when the coin price drops, the reward to the miners reduces, so the mining return on investment reduces for miners. So the miners, some miners stopped doing their business, which result in less hash power, which is much more easier for attackers to attack. So such a instability is really unacceptable for many businesses. And integrity versus privacy question. So in the enterprise blockchain, security becomes much more important, especially even compared with the traditional distributed systems, because there are multiple entities connecting and transacting each other, and those entities might have a conflict of interest in the transactions. And so there are many different requirements on integrity and privacy. On integrity, agreement on the transaction, validity, tamper evidence, and finality. Those are I think, the key requirements on the integrity side. And on the privacy side, if you look at the privacy in more detail, there are different levels of the privacy that people want. So the anonymity of the transaction to the third party is probably the easiest part. And sometimes you might want to have anonymity between the counterparties, or the confidentiality of the transaction content itself, or confidentiality about existence of the transaction itself, and the confidentiality of the state recorded on the blockchain, and so on. And so if you look at the typical cryptocurrencies like Bitcoins and altcoins that is implemented on top of the UTXO and proof of work or its variant in the public network, integrity is protected by, through the public verifiability, but without finality. And the privacy part is a bit more challenging, because many of them only guarantee anonymity because of the need of the public verifiability. The content of the transaction has to be exposed to the everybody, which is sometimes not acceptable in some use cases, because you can infer even without seeing identity, what is the kind of the transaction that is happening. So in the financial contract use case, this integrity and privacy requirements become more different. So on the integrity side, it's very much required that the participants are identified and authenticated. But transparent transactions should be validated not necessarily by everybody, but at least by all the stakeholders or all the counterparties in these transactions. That's the typical requirements. And typically, more stronger privacy is required. Depending on use case, transacting parties should be anonymous to third parties as a baseline. But in many use cases, content of contract and transaction should not be visible to third parties. So the permissioned blockchain networks try to address these kind of requirements by using sometimes different and sometimes similar approaches. One example is a private data collection from Hyperledger Fabric, in which only the public transactions and hash value of private transactions are broadcasted to all the participants and recorded on the public ledger, while private transactions are sent to the limited participants that are part of this transaction, and they're recorded only between them. And the scalability, so in general, public blockchain have a longer latency in general because of the need of enforcing random wait time to evenly distribute the validator across the network participants. On the other hand, it's in general easier to scale with a large number of the nodes. So, for example, in case of Bitcoin, I understand that there are approximately 10,000 nodes out there. On the other hand, in case of permissioned blockchain, because of the need of the business, higher throughput and shorter latency is achieved and aimed in general. On the other hand, because of the choice of the consensus algorithms, that it tends to be less scalable on the number of the nodes or peers. And if I give you some real-world examples of the requirements with claims that they process 1,200 transactions per second on average, and it can do maximum 24,000 TPS. And financial market post-trade case, on the peak time, such as right after the market open, they handle 5,000 TPS. That's a requirement. And many permissioned blockchain networks adopt the distributed consensus protocols because of the business need, which is traditionally called state machine replication. So basic idea is to make agreement among nodes without needing to trust any single node and to guarantee total order validity and integrity. And many of these algorithms are tolerant to failure, depending on the implementation. Some are tolerant to communication failure and crash failure, and many others are supporting the Byzantine failures. So this chart shows the example of the protocol in PBFT, which is initiated by the leader peer to start making consensus, and then each peer send the message each other, and finally come to the agreement after 3 phases and so on. And other protocols such as Raft and Paxos have basically the similar structure. So this type of the traditional distributed consensus algorithms are called order execute architecture, because we first make consensus about the order of the transactions, and then execute the transactions, and they store the resulting result into the states. So the problem of this approach is that because the transactions are ordered in advance, these executions has to happen sequentially, one by one, in order to guarantee the correctness of the result. And then there is no consensus over the execution result, because the consensus is made first and then executed, so that a smart contract has to be deterministic. So in the Hyperledger Fabric, it implemented a novel approach called execute, order, validate, meaning that we first execute the transactions by using smart contract in a kind of optimistic way. We call it simulation, and comes with the estimated result of the execution, and order these transactions and the result later, then validate them, and then commit into the database. So that the advantage of this approach is that we can do a parallel execution of the smart contract, which is often the bottleneck of the blockchain processes. And then we can also make consensus over the execution result, so we don't have to rely on the deterministic nature of the smart contract. It should be deterministic, but it can be verified through this consensus protocol. And because of this the architecture change, Hyperledger Fabric have achieved 3,500 TPS by using the use case called FabCoin or Fab token, which is an UTXO implementation on Hyperledger Fabric. And the last challenge is the safety of the smart contract. So smart contract is just computer programs, so it takes cost and time to develop. And it is often difficult to verify that the executable smart contract correctly represents the business level agreement. So this is problematic if you want to change the condition of the smart contract often, and this condition is agreed by the business level people who wants to make an agreement in the business level language or business level documents. And then they have to communicate the engineers to see if those requirements are correctly implemented in the smart contract. That's a very error-prone and time-consuming processes. And there is always a risk of bugs and vulnerabilities, such as the one we observed in the DAO incident, that can result in the huge financial losses. So that leads to the third topic of today's talk, which is a smart contract generation. So this is not a standard. This is a research work we do in IBM Research Tokyo. But we have made most part of the tools as an open source. But anyway, so the objective of this project is to streamline the smart contract lifecycle from the contract document to the execution and monitoring of the contract. And we use the formal temporal logic-based approach to define the correct behavior of the contract as a specification and generate automatically the executable smart contract that always comply with this specification. And if you already have a smart contract written in the programming language manually, we can also generate the monitors to monitor the state changes of this smart contract to detect any deviation from the specification, such as anomalies and incident. So we take a kind of stepwise approach from the contract document to the formal contract specification, which is converted into the state chart and then converted into the chain code written in Go language, and that can be deployed into the Hyperledger Fabric. Let me give you an example of the financial product called accumulator, which is one of the derivative product. So by the way, financial product contract is easier to handle on blockchain because there is no involvement of the physical world, which becomes much more trickier. But anyway, so this is accumulator derivative product is a kind of the financial contract. So there are sellers or issuers, sellers or investors who are the buyers that agree on the contract, and then the buyer agrees to buy the share of some underlying security at a predetermined strike price. And this number of the shares to buy changes by the closing price in the market. So, so for example, if the closing price of the shares, the securities in the market is below the strike price, the number of the shares to be bought is multiplied by the leverage, as you see on the third day of this chart. And if the closing price is bigger than the knockout price, the contract should terminate early before the maturity date. And the other days, this contract keeps adding 100 shares to the account of the buyer every day, and so on. So, and this state chart is an executable representation of the contract I mentioned. So basically, it consists of multiple states, such as day open state, day close event, and the arrow indicates the event. So upon the day opened event state, when the day closed event is received along with the closing price of the security, this price will be compared against knockout price to determine whether terminate early or to go to the next step. On the next step, the price will be compared against the strike price, and then additional share will be added to the buyer's account and so on. And this repeats until the maturity date or early termination happens. And in the business world, this kind of contract is written in the contract document, which consists of the master agreement and term sheet. And master agreement defines the basic terms and conditions, and it is used for multiple years, or at least long time. And upon each signing, the term sheet will be filled to provide more detailed parameters for each contract, such as the name of the underlying security, knockout price, strike price, and the maturity date, and number of the shares to buy every day, and so on. So when the term sheet is filled, we consider this is the agreement along with the master agreement. So in our approach, we take advantage of this structure of having a similar component for multiple the contract and having a limited variable part in each contract. So we take a contract template-based approach on both sides. So on the document side, we have a contract document template, which consists of the master agreement and term sheet template. And on the contract logic template side, we define the contract logic template in the temporal logic-based language called DSL4SC, or domain-specific language for a smart contract, to define the specification of the contract, but having some placeholders for the variable part. And if you look at the contract document, some of the contract document, the term sheet, include the simple values such as numbers and date, but some part is written in the natural language. So for example, in this example, the condition of determining the knockout price is defined in the natural language. So we took an approach of the controlled natural language to limit the vocabulary and grammar that can be filled into this blank. But because of that, we can understand the conditions correctly without ambiguity. So by taking this, from the when the contract is signed, we extract field data from the signed contract. Basically, field data is key value pairs, which is combined with the contract logic template and to make a complete contract specification written in DSL4SC. And then we convert it into the state machine definition and then chain code and to be deployed. So, and DSL4SC is a language based on LDL, linear dynamic logic, which is an extension of the linear temporal logic. So this language consists of the specification part and implementation part. On the specification part, we define protocols and properties. And the protocol defines the regular patterns of events to be processed by contract. In other words, it defines the valid sequence of events that should be processed by this contract. And the property part defines the temporal constraints on the states of the contract the contract needs to satisfy. So in other words, it defines a valid sequence of the states that contract should meet. And this is works as a kind of safeguard for the contract. So for example, you may want to say that some properties always hold or eventually hold or never hold, such as when the shipment is made, the payment is eventually made. It's a kind of the requirement that you want to enforce over the smart contract, no matter what logic is written in between. And on the rule part, we define the event condition action rules that define how to react to events. And we can also add the detailed implementation in a conventional language such as JavaScript or Go language. And here is an example, the web browser user interface of this tool. So we can see the table view of the list of the contracts that are deployed on the blockchain. And if you click on the show state button, it brings up another window to show the state machine and highlight the current state in color, and also show the list of the variables that are stored in the state, and so on. Yeah, let me skip this. So this our tool have many values. So today's pain point of smart contract needs to be deployed by human engineers can be reduced because the contracts are automatically generated to reduce the time and effort for development. And the risk of the errors and the threats can be reduced because we can generate smart contracts that always satisfy the safety and liveness properties defined in DSL4SG. And the third is business or legal people wants to make agreement in a natural language, but it's difficult to communicate with engineers, or not difficult, time-consuming or effort-consuming to communicate with engineer to verify, to correctly implement it, and to verify that they are consistent with executable smart contract. But now the user can define the terms and conditions in a controlled natural language, which can be translated into the smart contract using template-based approach. So conclusions is that there are, for permission blockchain, enterprise blockchain in general, there was a period of the hype and the proof of concept, but now the serious production systems are emerging and growing. But still, there are many challenges to be addressed, which is kind of the good things if the industry and academia can collaborate. And the last remark is that this DSL4SC is published as open source, so we are welcome any trial or feedback and comments and so on. Thank you.
Thank you very much. Okay, we have a few minutes for questions. Okay, gentleman over there. Chena.
Thank you for your presentation. I have a question about the power of the temporal logic-based language. Is it enough power to really prove the safety and liveness? And could you tell something about the verification of the smart contract or formal specification on this level? And I would like to ask that the smart contract could be very complicated, and there are too many safety formula that couldn't be resolved. And do you have some restriction? For example, do you have restriction for the number of agents, in the contract? It's also a problem, and this is my question. Thank you.
Yeah. So for the safety part, we can verify anything written in LDL in terms of the property specification, and this verification happens when the smart contract is generated. So any contradicting the contract won't be generated. That's a guarantee we have. And for limitation part, we are still testing this for our real-world use case. We started with smaller examples and gradually expanding it to cover a real-world contract, such as the real-world securities term sheet or real-world. By the way, the derivative example is a little bit simplified, I guess. Or other types of the contracts such as insurance policy and so on. And the one unsurprising observation is that if the contract and requirement becomes complicated, the number of states drastically increases, which makes it more difficult to verify and generate. So basically, it takes very long time. So that's something that we are still working on.
Okay. Okay, gentleman back there.
The speed up for the the supply chain tracking application from a week down to 2.2 seconds is very impressive. But it might also have been achieved just by having a database rather than a blockchain-based solution. So can you talk to the question of just what statistics do you have on the types of fraud and the amount of fraud that happens in these supply chains that the blockchain-based solution is providing protections against that a database solution would not?
So I think the question is the number of the fraud on the supply chain network before the blockchain is adopted. Okay, I don't have any detailed statistics except this one. Probably many frauds are invisible, I guess. But the more than fraud, there is a lack of the way of exchanging or sharing information in a transparent manner. So basically today, the information is not shared. Information is managed only by each company and exchanged in a pairwise manner. So it's very difficult to detect any kinds of frauds when it happens. Right? But it changes because of the increased transparency. Did I answer your question? I'm not sure.
So if the fraud is difficult to detect, I mean, it's like, so if the fraud case happens after all, then the authority, it will be eventually reported to the authority, right? So, so we can simply compare something like a before and after test. So, so if the blockchain has been adopted at some point in the time, then so is somebody collecting some data like, so okay, let's have this company A, and this company A has started adopting the blockchain, let's say 2017, January 1st, something like this. So before that, these companies have been involved in a certain number of fraud accidents, and this company, after the adoption of the blockchain, has been involved in that number of fraud incidents. So are somebody collecting these kind of active statistics about some kind of A/B test about how blockchain is effective in curtailing these fraud incidents? Do you have any knowledge about those things?
I doubt if there is any good statistics because if the company has not discovered their fraud yet, they don't want to disclose it, right? and especially large companies who are already participating in this network are not very keen on frauding itself, but rather they want to prove their integrity, their business integrity. And then they probably much smaller companies tend to do more fraud, but many things are underwater that you don't see today. So we see those news when the fraud is discovered and it becomes a social issue or something. But that's kind of spot events that we don't see much more structured statistics every day.
So then. Can I understand this as it for some time at least it will not be that easy to measure the effectiveness of the blockchains in curtailing those fraudulent incidents, right?
That's my guess, but yeah, that's I think very good point that I'd like to validate with my colleagues who are actually working on this project.
Okay, last question, Saleh?
Hey, yeah, thanks for your talk. So in the same context, the food ecosystem, right? What are your thoughts on how do you verify the data that's actually being logged, right? Because in your example, you talked of the mango. I mean, the mango grower might claim it is organic, but how do you know?
That's a very good point. So there is a last part of the missing link between the physical world and the the digital world. That's something that we cannot address only by using blockchain. And IBM is working on other technology to increase the trust of the IoT. So for example, we work on the very small computers that is as small as the salt grain or something that can be attached to the physical object to prove the authenticity of the object and so on. But proving if the mango has been grown in organic way or not is much more difficult than that, just identifying the physical object. So I think the blockchain is not a silver bullet for that. We need other technologies to fill the gap.
Okay, I'd like to thank the keynote speaker, Sachiko, and present her with a small gift.